Hello and welcome to Apache TinkerPop's home here on Twitch. Today we have another TinkerPop Wide stream where we explore the wider TinkerPop community by taking a look at tools, libraries, or graph systems built on the TinkerPop framework, or even applications built on those foundations. Today we'll be learning about a particularly I say exotic graph system called ChronoGraph, which is TinkerPop enabled. It is a time-oriented graph developed by Martin Häusler, who's here to tell us all about it. Thank you for joining us today, Martin. Really appreciate you being here on the stream today to talk about this.
Thank you for having me.
Just before you get started, just a reminder that we'll be monitoring both the Twitch chat and Discord events channel for questions, and we'll get those posted to Martin at the end. So with that, I will kind of back out of the way and let you let you go. Let me get your slides up on the screen here.
Perfect. Thanks.
I think we agreed on this style here, and I will leave you to it. Thank you.
Yes, so hello, ladies and gentlemen. Good evening, good morning, good afternoon, all over the world. My name is Martin Häusler, and we are going to talk a little bit about time traveling with Gremlin and ChronoGraph today. So I'm 33 years old. I'm talking to you from the beautiful city of Innsbruck in Austria. In my professional life, I'm the lead backend developer at Text.io. Where ChronoGraph is also used in production, and some of my hobbies include software design, game design. Also, I do a lot of Dungeons and Dragons stuff, so there's that. Language-wise, German, English, Java, Kotlin, of course, Gremlin. You can reach me on GitHub, you can reach me on email. And with that, enough from myself, so let's dive into the topic. So what is the Chronos project and what's the goal? Well, the aim is to offer reliable, embeddable, and easy-to-use version storage to the JVM. It started as a research project, in fact, my PhD project, but now it's used in production and it's hosted by Texture. So here's the rough architecture. The rough idea is you have several layers, and each layer builds on the layer beneath, but you can use the layers also individually and place your application wherever it is suitable for you. Today, we are going to focus mostly on ChronoGraph and also a little bit on ChronoDB as it builds on it. So before we dive into coding and stuff, let's do a little thought experiment. Does anybody remember these things? I don't know, maybe I'm just old. Those are called overhead projectors. And the idea is you have a light coming from below, and you can put a transparent slide on it, and it will project, like the image, as you can see here, onto a screen. So what does that have to do with anything? Well, let's imagine we have such a projector area, and we have a stack of transparent slides, and we draw a graph, basically, on those slides. So as you can see here on the left, I've prepared a couple of slides. And what happens if I move the slide onto the projector? Well, it will get projected on the wall, right? And if I put another slide on top of it, you can see we got a new element into the graph. And then we get the third slide, and the graph just grows and grows. So this way, we can achieve basically snapshots of the graph. And we can also do this backwards, right? So we can go back in time by simply removing slides from the top of this stack. And each stack of slides, starting from 1 and going until X, is a consistent snapshot of the entire graph, always. And since it's consistent, it's no surprise that we can actually run gremlins on each of those slide stacks, right? So, and depending on which height you choose, you will get different results for your gremlin, because depending on the height, there will be different elements present depending on what you have drawn on your transparent slides. So you might not argue, yeah, but when you always can add and add and add, how do you do deletions? Well, for deletions, we need to pull a little trick. Since we cannot just go ahead and erase things from previous slides, we are going to use deletion markers. So we just cross out the elements that we no longer want to see. And if we put that on the stack, then you can see those two edges and this vertex would be gone and no longer considered. And that's the basic principle of versioning. So you have the slides, which are basically transaction commits. You have the slide numbers, and we are not going to use arbitrary numbers. You could, but we are going to use timestamps, so they actually make sense in the temporal way. And then you have the projector area, which is essentially just your graph content. So why would you do this? Versioning is a niche feature, I will admit that, but when you need it, you really need it, and you really can't do without. Use cases include traceability of changes, so who changed what and when, like down to the very minute details. For auditing purposes, for compliance, when the law states that you have to provide this data, you cannot avoid it. There are regulated environments where this is the case. And you can also do fancy stuff like trend analysis. So you can observe, okay, how did my graph evolve over time? And then you can try to make a prediction how it's going to continue its evolution. Keep in mind that versioning is not the same as time series. I get this question a lot. And time series databases like Prometheus, for example, they are focusing heavily on aggregations over time. So you take a period of time, you take measurements, and then you aggregate. Versioning is not the same. Versioning is concerned with consistent snapshots at any given time. And the snapshot really goes across your entire database. So that's the difference. How do we code with all of that? Well, just yesterday, actually, I published the newest version of ChronoGraph and the entire Chronos family, version 1.3.7. And you can just grab it from Maven Central. And basically what you get with the ChronoGraph alone is you get the graph layer and you get an in-memory backend. If you also want the file-based backend, you need to include the Exodus backend as well. Exodus is a neat library provided by our friends at JetBrains, which provides a key value store essentially, and we're building on top of that to provide file-based storage. For our examples, I will not show every time how the graph is created because it's always the same. You can see this small code snippet below. You just say you have your graph factory, you choose whatever backend you want, so in-memory, Exodus are the default ones, but you could also implement your own backend if you so desire. And then from there on out, it's a regular Gremlin API. And like I said, in-memory is provided by default, and JetBrains Exodus can be added with a dependency. So what does it actually look like to work with ChronoGraph? Well, as you can see here, we are building a small little graph. We open a threaded transaction, so we do support threaded transactions. And actually, I would encourage everybody to use exclusively threaded transactions, thread-bound transactions, because they're way easier to manage and easier to track, like what's happening. It's explicit, and that's good. So here we're adding a vertex. We're adding a person, John Doe, and another person, Jane Smith. And we are adding an edge between them. And Jane becomes a contact of John. And the type of this edge is a friendship, and then we commit the transaction. Note that there is nothing special in here. This is 100% your regular Gremlin code. There is no particularities. You can't tell that you're working with a version graph database here. Next, we are going to open another transaction just to have some data available to us. And we're going to have John and Jane married. So we change the type of the edge from friendship to married, and we change the last name of Jane from Smith to Doe, and then we commit again. Again, nothing fancy here yet. So what we can do now, thanks to the power of ChronoGraph, we can actually inspect the histories. So from our transaction, you can query the vertex history of John and Jane individually. Or you can even query the history of the relationship edge between them. And what you get back initially here, as you can see in the console output below, is a list of timestamps. And now you might say, yeah, but what am I supposed to do with timestamps? Hold on, that's going to come very soon. But first of all, I wanted to show you that with the regular Gremlin API, you can have ChronoGraph track everything for you, and at no extra effort on your part. In fact, if you're using a standard Gremlin graph database, you could even take that and replace it with ChronoGraph, and you would have no issues as long as you do not use any vendor-specific extensions like these. What we can do now is we can actually go ahead and say, yeah, let's have a query. Let's have, for example, this traversal.v, we are looking for a person with first name John. Then we traverse both outgoing contact edges until we no longer can, as both the incoming and outgoing. And then we basically get the first name as base and the last name of whatever person we find. And now we do this twice. First, we do it with a regular threaded transaction, so on the head timestamp, so to say. And if we call our little analysis here, then we only get John Doe. Why? Because we changed the type of the edge from friendship to married in our latest commit, right? That's why we only see John Doe, because there are no contacts anymore, just the person he's married to. Now here's the deal. We can look at our commit history and go back to the previous commit. So we get the commit timestamps before our current timestamp, go back one, and then we use this head -1 timestamp to query again. So we run the same query, but we remove the top slide of the overhead projector, so to say. And what we get now is we get the previous state where John and Jane have not married yet, and now we get the relationship with the friendship again. So at head -1 at the previous timestamp, we get John Doe and Jane Smith because they are still friends and not married yet, right? And in this fashion, you can go back not just one commit, but arbitrarily far. Also, arbitrarily far as long as ChronoGraph was able to observe the evolution, right? You cannot go further back than when you started using ChronoGraph, obviously. Also, you do not have to hit the transaction timestamps exactly. You can provide it with any timestamp, and it will default to the next lower commit timestamp that there is. So this way, we can really travel across time and run our queries on any snapshot that the user desires, basically. Yep, I think I said all of this. Noteworthy here is also that the query itself did not change. That's why I put it into a separate method to really demonstrate and drive home the point, hey, the query is always the same. It's the data that's changing, and that's why the output is changing, right? Another example, you can actually, if we produce, like here we're iterating 10 times, and we're creating 10 transactions, and we are all creating and or altering the same vertex the whole time. So we change this property I of the vertex, and we increase it every time. But you can also see that when we commit the transaction, we provide it with additional data. You can think of this as a Git commit message, for example. Internally in the API, this is called commit metadata because it can be any object, not just a string. But let's stick to strings for now because it's easy to demonstrate. So, and after we have created those 10 commits, we can now query them. And how do we do this? Yeah, well, we fetch the commit metadata after a certain point in time, in this case after 0, so we'll just get everything. And then we iterate over the commits, and then you can see what the metadata corresponding with the commit looked like. This is a neat feature. You can use this in a wide variety of ways, but commit messages are usually one of the common use cases. Now you might say, well, it's a little bit tedious if you have to manage all of those transactions, and when you iterate over the history, then you have to open a transaction on each of the points in time and so on. And yes, you're right, that is a little bit tedious. So I provided a builder syntax with this create iterator, where you can say, okay, I want to iterate over the history of something, in this case over the history of vertex v1. And then there is the visit coordinates method that provides you with a pre-initialized transaction, and you can start reading from it right away. This is also great if you want to do comparisons, like computing the diff between two commits on a vertex. You can also use this API for that. And as you can see, this property I that I talked about earlier, which we increased for every version of the vertex, indeed has different values depending on the timestamp that we're querying. So it's a really neat feature that you can just go anywhere back in time, and you will have the full power of Gremlin available to you to query the data. I think that's really neat. For the third example, it's getting a little bit crazy. So first of all, as all important Gremlin implementations, of course, we do have indices, secondary indices. And we have them for strings, we have them for longs, we have them for doubles, as well as lists, sets, and arrays of all of those types. So you can have multi-value properties. you declare them basically on a vertex or on an edge, and you provide it with the name of the property that you want to index. And when you're done with creating all your indices, then you call it reindex all once, and then the indexer will run through your data and collect all the values and then build the secondary index for you. I guess that's a fairly standard procedure. And these queries these indices, they are sparse. So if vertex does not have the property name, for example, then it will not show up in this index. This was done to conserve space mostly. And also, since we don't know the schema of the data in advance, there is no way of telling how many null values you're going to have. So we are just not indexing missing properties and null values at all simply to save space in the index. And the optimizer then can utilize this index automatically. So when you do a traversal and then ask for has name John and name is indexed, then Gremlin will automatically utilize this index to answer the query. Again, fairly standard procedure. So let's add some data, and now it's getting a little bit funky because we're now entering the realm of branching. I'm going to explain on the fly like what this is. So I hope that there are some Marvel fans among you. So we start with our basic first commit, with our basic first branch. And we are going to insert a vertex for Loki, who is an Asgardian, and for Wanda, who is a human. All right. Then we commit that. So far, nothing special. Now we are going ahead and creating a parallel universe. We're going to create a branch based on this initial commit. So we are branching off into a parallel universe, and in this parallel universe, Loki is an alligator for whatever reason. And then we commit again. And the branches in Chronos follow the same principle as the branches you might know from version control systems such as Git. So the branch contains all the data of its origin, but the modifications on the branch are not visible on the origin anymore. So I can now make modifications to universe A without disturbing any data in the main branch. They are intended for what-if analysis, for sandboxing, for planning, and other use cases. At the moment, there is no way to actually merge them back because that would be kind of difficult to maintain the graph integrity at the same time as merging. And you can create those branches, first of all, from any other branch, and second of all, at any timestamp. So wherever you are in your flow, you can always go there and create a branch from that particular point in time, and the data will then be available to you. Branches can be nested arbitrarily. Please don't overdo it because there is some performance cost to branching, of course, because it's an indirection. So if you nest them too deeply, you may incur a performance overhead at some point. But the number of sibling branches actually has no impact on the performance whatsoever. So you can have 100 branches which branch from the same origin, and that's totally fine. The branch which you want to query is actually chosen when the transaction is open. So when you open a transaction, you can choose two things. First of all, the timestamp, that's by default is the head, the latest version. And second of all, the branch you want to target with your transaction. And by default, that's the main branch, but you can choose any sub-branch as well. So universe A here in our example. Branches are lightweight, which means when you create a branch, even though it looks like you get your own copy of the data is actually not duplicated on disk. So it's reusing the data from the origin branch. Why is that possible? Because the history never changes, right? So when the data is written and it's in the history, it stays in the history, no matter what is added on top of it. So we can reuse the existing state and redirect your requests that cannot be answered on the branch itself to the origin transparently. So let's go a little bit even more crazy and create another universe, universe B, again, branching away from the main branch. And in this universe, Wanda actually has two children, child 1 and child 2, and she's the mother. And as a final example, let's go back to the main branch. So we have the main branch, we have two sub-branches, and now on the main branch, we add another vertex. In this case, we add 4, who is also an Asgardian. And the structure that we created is pretty much this one. So first of all, we added Wanda and Loki as our two verses initially. Then we created the universe A and universe B commits. And then we added another one to master. And now we're going to query all the 3 branches at their latest point in time and see what data we actually get from that. And this is what our little analysis code is going to look like. So we passed a ChronoGraph, which is initialized with a transaction. So first of all, we check out which branch we're on to print it to the console. Then we are going to get the commit timestamps on this branch and see what we get. And then we are going to look for Loki for Wanda and see what the, first of all, do they exist? And second of all, what race they have. Because for Loki, the race, if you remember, actually changed. And also for Wanda in particular, we are interested in if she's a mother of any children. So in one of the universes, she should actually have children. So the rest is fairly standard Gremlin API, I would say. And the rest is just print lines, essentially. And this method we're going to use now on all the 3 branches. So what does that look like? Yeah, well, we ask our branch manager, hey, please give me the names of all the branches. And then we start for each of the branch names, new threaded transaction. And as you can see in the code example, we provide it with the branch name we want to operate on. And then we have a fully initialized graph transaction. And then we pass it to our inspect universe function. And now, as you can see in the console output for universe A, Loki has raised alligator because that's what happened to him. 4 doesn't exist. So if we go back again, as you can see, 4 was added on the master branch. So it's not on universe A at all. It doesn't exist. And Wanda has no children. Yeah, well, Wanda's children were added in universe B. So universe A would have no idea about it. If we inspect universe B, then Loki is still an Asgardian because it turned into alligator in universe A. 4 doesn't exist. It only exists on main. And Wanda has children, child 1 and child 2. So you have really the full spectrum of graph analysis capabilities that Gremlin provides available to you in the context of branching, in the context of version control. And in the master branch, finally, Loki is an Asgardian, 4 is an Asgardian, and Wanda has no children. If we check back, yeah, Wanda's children were added on universe B, and Loki is an alligator on A. So it only makes sense that on the main branch on master, Loki and 4 exist. They are Asgardians, and Wanda is a human without children. So that's the gist of it, right? That's the gist of branching. So branches can also be nested. So from universe A, you could create universe A1 or universe alpha or whatever you want to call it. And you can do this like arbitrarily deep. But like I said, you will incur at some point a performance cost depending on how big your graph is and how sophisticated your queries are. Now you may be asking, how is that working? And indeed, it is a little bit special. So we can treat this entire problem as a matrix. On the x-axis, we have the time, and on the y-axis, we have keys. So at the end of the day, we can map our graph to a key value store. I guess that's fairly well known because that's how most graph engines out there operate. Eventually, everything gets mapped to key value. The difference is that we are having another dimension to deal with. So usually under key and value, we have time and key and value. So let's assume we have a transaction at timestamp 1 and we insert some data. In this case, we insert zeros, but all of those orange knobs might as well be vertex information or any other byte array. We don't know. We don't really, to be honest, we don't really care at this point what it is. So let's assume it's just a 0. All right, then at timestamp 2, we insert value 1 for A and the rest we copy. At timestamp 3, we insert a value of 2 for key B and the rest we copy. At timestamp T4, we delete key D and the rest again is copied. And at transaction timestamp 5, we insert a new key E with value 3 and the rest is copied. As you can see, and as you can probably imagine, from this structure, it's easy to go back in time and query the past simply by selecting a different column, right? So if you're interested in the data at timestamp 4, you can just look at the matrix, scan the column basically, and grab each key value pair individually. Mind you, do not pick the key D because D was deleted, as you can see indicated by the deletion marker. So we do not include it in the results. That's the only thing you really have to be mindful of here. If you're interested in the history of a single key, like for example a vertex or an edge, you just have to traverse it horizontally, and you will get all the values of this particular key. And if you're additionally checking the time axis, you also get the timestamps when it changed. So that's that. And this representation is nice because it can answer all of our questions, right? but it has an extreme amount of data duplications. There are tons and tons and tons of duplicate entries in there. And that's not good. That's not good for persistence. That's not good for performance. We don't like to duplicate data all over the place needlessly. So the core observation here, like I said before, the history doesn't change, which allows us to reuse previous entries. And that looks like that. So I call this these gray boxes validity periods. So each key value pair is valid until a new value arrives for the same key. So for example, the pair D0 starts at timestamp 1 and ends at timestamp 3, because at 4 we have a new value for D, which is the deletion marker. So the deletion marker counts as a regular value in this case. And now that the duplications are almost entirely gone, there is a small catch here, but for the most part, they're gone. And if we want to query the key D at timestamp 3 again, what happens? Yeah, well, before we just looked at the right column and the right row, and then we checked the value that was there. It's a little bit more complicated now, so we still start at the row at the column, and then we move in to the cell, and then we find okay, we have no value for this cell directly. However, we are part of a validity period. So now we scan to the left and see what value we find. And so eventually we find the value 0, which is the correct result and the same result as before, just without all of the duplications. If we look for B at timestamp 2, again, same trick, we end up at this empty cell. And we again try to move left, but we find nothing. And why is that? Yeah, well, at timestamp 2, key B did not exist. It has never been inserted into the store yet. So it's actually key not found, which is the result of this query. And it's the same if you do it on the validity periods and in the original matrix. It doesn't change. Okay, another question you could ask is, give me all the key value pairs. Do a full iteration over the entire graph. Yeah, okay, sure. We start at timestamp 7. We look at all the keys in the matrix, so we move up as far as we can. And then what do? Yeah, again, we move left. For each key, we move as far left as we can. And again, keep in mind that for key D, Dora, we have a deletion marker, which is why key D is not included in the result set. So now that we have agreed that this matrix thing is very useful for storing version data, how do we do this? Yeah, the time key value matrix is a 2-dimensional matrix, which is infinite in both directions and very, very sparse. So most cells will be empty. In fact, as long as you do not receive any commits, the timestamps will still continue to count and count and count. So Unix epoch millis, right? They just keep going and keep going. And eventually you have a commit. And then one of the columns may include a couple of new values. But for the most part, like 99.99% of this matrix will forever be empty. So the hard drive, on the other hand, is 1-dimensional, has finite storage capacity, and works best with tightly packed data. So if you have a lot of zeros in your file that you're not interested in, then your file will be needlessly big, right? So all of these are kind of problematic. So we have to invest a little bit of work here to actually efficiently store this time key value matrix, right? So the first step is take this visual representation and turn it into something that is more computer-like, something that computers can deal with. Let's turn it into a table. So we have the key, the time, and the value as the 3 columns. Again, the only speciality here is for the key D, the deletion marker that we have to use an extra value for, but that's not a big issue. And the key observation now is that the key and the time together, they're unique. So you will not find 2 rows which have the same key and the same timestamp. So we can combine them. In this case, I just combined them with a string concatenation with an at in between. In reality, it's a little bit more complex than that, but that's the gist of it. So we combine them together, and the combination we call a temporal key. So it's the key plus the time, thus it's a temporal key. And from here on out, we have a usual key value store, right? And we know how to handle a key value store. We can put them into a B tree, B plus tree, string sorted table, what have you. We can use all of those standard techniques again in order to accomplish our goals, to store this matrix. One thing that's crucial here is the sorting of the temporal keys. We store always first by key and then by timestamp. And this sorting needs to work in the binary format too. This can be efficiently implemented, but it requires that all the keys have equal length. ChronoGraph uses UUIDs by default. You can use custom IDs as well, but if you do that, you are responsible for ensuring that the keys all have the same length, otherwise things will break. So why is it important that we have this sort order? Well, let's try our query from before again. Give me the value of key D at timestamp 3. We search for D at 3, obviously, but as you can see in the table, it doesn't occur. It would be here, but it's not. So what do? Yeah, in the matrix, we move left. So in the case of this table, we move to the previous entry, which would be the one before. We're always interested in the next lower entry. And if it has the same key, we return the value. If it has a different key, then we did not find the key we were looking for in the first place. So in this case, we find D, which is the same key as in our query. And the result, therefore, is 0, the value associated with this temporal key. If you're interested in the nitty-gritty, into really the details of all of that, there is a paper from my PhD times, which is on Springer, which is totally accessible to everybody. You don't have to pay anything for it. You can just click the link and you get a web page, or you can also download it as a PDF. It includes ChronoDB, it includes ChronoGraph, it includes a lot of information that I cannot cover possibly in this live stream here. So for any further reading, please feel free to check that out. Some of you may argue now, well, can we realize this with regular SQL? And also to maybe drive home the point a bit why I did all of this myself and not just used an existing topology. Sure, you can do this in SQL, no problem. You have a table already, right? Tables are great for SQL. So you can do a matrix table. And you can even create an index on the time column and so on. And the primary key is just the combined key of key and time. No problem. But what happens if you want to select something? Well, there is this standard procedure. You do select from where, blah, blah. The tricky part is choosing the right timestamp. There is this timestamp that you get from the transaction, which is like the one you're interested in. But maybe the value you look, or maybe the temporal key you're looking for, like in the example before with D at 3, does not exist precisely in the table. So you would need to look for the next lower timestamp for the same key. And the way you do this in SQL is by using this subselect here. And this subselect is not just any subselect, it's a correlated subquery. And correlated subqueries are slow. So not only is this query very complex for the simple thing it tries to accomplish, it just fetches an element by ID, it's also very slow. So we cannot really use existing databases for this. There are some commercial databases that handle this kind of query. For example, I know that SQL Server has immortal tables, as they call it, which is a different implementation of the same concept. But for the open source databases, I'm not aware of any SQL database that can actually do this. So in my PhD, I said, OK, I'll go ahead and do this myself. And thus, ChronoDB was born. And ChronoDB handles exactly all of this matrix handling and timestamp resolution and so on. And on top of ChronoDB lives ChronoGraph. And it's quite easy to imagine, because that's not really special in ChronoGraph. The way we serialize the data is fairly standard. In fact, I looked back then at TitanDB, how they how they disassemble the graph into key value pairs. And ChronoGraph is very much inspired by that. So there is nothing too special on that layer. Then we take this piece of the graph, this edge, this vertex, we throw it into Creo, so we get a byte array, and the byte array is then stored in the matrix. And there are 3 different or 2 different backends that are implemented, like I said, in-memory and Exodus, but you can also create your custom backend. So the interfaces are there. If you want to, feel free, go ahead. On top of ChronoGraph, we have Gremlin as our graph querying interface. And then on top of all of that sits the application. And the important thing is all of that is running in the same JVM. The advantage of that, obviously, is ease of deployment, ease of use. When you have a distributed graph system, like Janus Graph, like Titan on a Cassandra cluster, for example, then you have a much more complicated deployment. There are also other concerns, such as ACID constraints and so on. But for the most part, it's about ease of deployment. And also, when you have the database in the same process, then you can also do things like iterating over vertices and their edges in memory without transferring them over the network the whole time, back and forth, right? So this issue is a lot smaller in an embedded database. For texture, this has already been, the place where I work has been really important to have it embeddable, to have easy deployments, essentially. So another problem that we are facing when we are collecting data, so every timestamp that is added, every commit that is done increases the size of the store, right? It never gets smaller, it only ever gets bigger because the history gets longer. So even if you do commits, in the background there will be additions to the matrix. So the history will grow and grow and grow. And eventually you have a huge history, but the query you're dealing with is only interested in a very small slice of the history. And there is a lot of data that's actually not relevant to the query you're looking for because it's older versions or newer versions, depending on the choice of the timestamp, right? So how do we deal with this? Because B trees are cool and all, but eventually even a B tree will get slow, let's face it. So what we do is a sort of checkpointing. We call this rollover. You will see in a moment why. So we have the head timestamp, and then we accumulate history and history and history. And at some point, we say, okay, that's enough. Like 90% of our data chunk consists now of historical data and only 10% of really the head timestamp. So what we do is we take the head timestamp, we copy it essentially into a new empty matrix, and then we go from there. And as you can see, we roll over the head into the next chunk. The only thing we have to keep track of is which chunk contains which timestamps, so which period of timestamps lives within which chunk. But the old chunks are never modified again. That's good. And by having this time range lookup table, essentially, so we know timestamp 0 to 1000 lives in the first chunk, 1001 to 2000 lives in the second chunk. The periods also don't need to be equally sized, not at all. As long as we have this information, we can always redirect each incoming query to the correct chunk. And also, fun fact, this chunking mechanism is not only done on the master branch, it's done on all of the branches. So yeah, this helps us to maintain very, very long histories very efficiently. Speaking of very long histories, the largest ChronoGraph production instance has over 300,000 vertices in the head version alone, has over 1 million edges in the head version, over 30 properties per vertex, and contains over 3 years of history, of real production history. And it contains almost 300 gigabytes of data. So there's been a lot going on there. It uses the JetBrains Exodus backend, and it runs on a cloud VM. So this thing really is used in production quite successfully, I would say. What about the code base? Well, we are dealing with around about 60,000 lines of Java code and about 10,000 lines of Kotlin code. So when I started the project in 2014-ish, the Java was all there was for the JVM, pretty much. So I started with Java, but over time I really started liking Kotlin more and more and more. And I dare say that the 10,000 lines of Kotlin code you see there accomplish almost half as much as the 70,000 lines of Java. So Kotlin, really a cool language, really nice. What about licensing? ChronoGraph is dual licensed. So there is the HEPL license for all the open source folk out there. So as long as you're open source, we are open source, you know the drill. It's unlimited access. If you want to use it commercially, please get in touch with me. Regarding the road ahead, so what's next? The existing solution has issues. I'm the first person to admit that openly. First of all, the ChronoDB layer operates on arbitrary byte arrays. So it does not care about the inner structure of the data. In fact, ChronoDB has no clue about vertices and edges. It just deals with byte arrays, which makes it difficult to introspect the data. It limits the optimization possibilities. It's a drawback for performance for that reason. Creo has been a poor choice as well because they're not backwards compatible. The format changes, so you can, and Creo 3 is not updated anymore. So that was definitely a mistake. The solution is, of course, to take control over the serialization format, and I'm going to use documents, and I'm going to show you a little bit more about that in a moment. The second problem is that not all data needs to be versioned. There will be some data that needs version control and some data that doesn't. But still, you want to use the same database system for both. ChronoDB cannot do this. ChronoDB simply versions everything by default, and you cannot turn that off. In the new solution that I'm thinking about at the moment, there will be areas of the data which are versioned and areas of the data which are not. So they act like a normal graph, essentially. And at the moment, the optimizer is quite limited because it has no statistics available to it. It does not know how many vertices of a certain type you have. It knows nothing about the schema. We are entirely schema-free. The consequence is that it can only perform data-independent optimization, so the kind of optimization that always works. Like, for example, true and false is a contradiction. That's the kind of optimization you can do. But that's about it, plus the secondary indices, of course. The solution is to keep track of the data schema and statistics and guide the optimizer with that. I'm not saying that we want to have a predefined schema. I'm just trying to say that we have to keep track of the schema in some way. And the final point that on this slide, but I'm sure there are many others, when I started working with TinkerPop, there was no notion of this vertex layer. It just did not exist back then. There was a very old version of TinkerPop. So all the vertices in ChronoGraph end up in the same store, in the same B tree, which is bad. If we had some sort of type system where you can say you have vertices of type person and vertices of type something else, you could split them up into different B trees, and the individual querying of those trees, since they're smaller, would be faster. So that's definitely something I'm going to do. And the vertex label, of course, lends itself very well to this kind of concepts. Also, since we are going to split up the data, we can support more types of indices, also non-sparse indices, because we have a better idea, better understanding of what our schema is going to look like. And like I said, there are, of course, other things, but you always learn over time, right? And those are the things that I learned the hard way. Yeah, so the next solution that I'm currently working on is called ChronoDocs. It has a better data layout. It uses Bison, so the binary JSON format, for which I've written a custom serializer, deserializer, which is called Hornox. You can find it there. It's an open source library. Check it out. It's quite fast. It's actually faster than the MongoDB Java library, and it's for serialization, deserialization, and it's also faster than the Bison module for Jackson, which is a very popular framework. So yeah, there's that. I'm going to support more indices, like full, partial, unique indices. There will be support for different collations to ignore things like upper, lowercase, stuff like that. There is at the moment in ChronoDocs, in ChronoDB, the possibility to have case-insensitive queries, but it's very basic, I would say. If you're dealing with umlauts and stuff like that, or even, I don't know, Japanese characters or whatnot, that's not going to play out very well for you because it's too strict. So collation will help to alleviate this problem. There will be a better optimizer based on document schema and actual statistics that we're tracking, which at the moment I'm not doing, but I will. There will be better support for queries. At the moment, ChronoDB at its very lowest level only supports very basic queries where you can essentially scan the index and do some ands and ors, and that's it. For ChronoDocs, it will be MongoDB-inspired query language with a lot of operators. And Gremlin will then be implemented on top of this new mechanism. And finally, there will be selective versioning. So you have collections like in MongoDB, and for each collection, you can say, this one I want to be versioned, this one should not be versioned. So you actually get to choose. So that's ChronoDocs in a nutshell. My personal wish list before I end the presentation here for Gremlin 4.0 really quickly. I was struggling as of late with traversal unions. Feel free to check out the link there. There is a proposal there. I was struggling to filter elements by type, which was surprising for me. The only solution we have right now is to use a lambda filter, which is a little bit iffy. I would very much love it if the TinkerPop test suite would allow each test to be executed individually. So at the moment, you can just run the entire suite or nothing, which is annoying when you have to put breakpoints in there. So that was a bit of a pain during the development. I would love it if Gremlin would provide standard predicate optimization. So things like you have a within clause, you have another within clause. Okay, let's intersect them because they both have to match. So only the intersection is interesting and not the entire rest. Or you have a within clause and an is clause, so the is clause wins if it's inside the within. Stuff like that, double negation elimination, De Morgan, conjunctive and disjunctive normal form, all of that stuff that at the moment each graph provider has to build individually. It would be very cool if we could get integrated into Gremlin, so we have one common standard we can agree on how to optimize our queries. And finally, I would love it if Guru and the shaded checksum that comes with Gremlin would actually be gone, simply because they're magnets for vulnerabilities. So I've done many upgrades for ChronoGraph in the past, which were simply checking for vulnerabilities time and time again, and almost every time the shaded checksum showed up somewhere. So I would definitely not be sad if this thing was gone. Okay, that was my wish list. To summarize, time traveling with Gremlin, it's basically those overhead slides that you stack on top of each other, and then you can remove slides again from the top to go back to previous versions. Version control is essentially time traveling plus the branching aspect, and ChronoGraph provides embedded Gremlin with the version control aspect. So, folks, I'm a little bit over time. That's all from my side. Stephen, do we have any questions?
Yeah, I definitely have some questions. I think, I mean, first of all, I mean, what sort of inspired you to do a version-oriented graph in the first place? Were you working on something, or you just kind of fell out of the sky on you? What happened?
A little bit of both, actually. So it was my research project, right? So I had to do something academic and research oriented. That's what we do. And I was working in this field of model engineering with the Eclipse modeling framework and so on. And it still shows today because the layer built on top of ChronoGraph is Chronosphere, which supports all of those modeling techniques. And back in the day when I was building this thing, unless you had versioning and version control in the academic world, your tool did not even exist. So that was like the baseline requirement for all of those tools. And I wanted to build such a tool. So I knew from the get-go that I needed versioning. Then over time, when texture came around, and it was really fortunate that we had this version control thing, because texture users love the version control and the timelines they get from it, and going back in time, and also they use branching extensively and so on. So all of those features really are used. You would not believe it.
Yeah, very interesting. I definitely learned a few things. I had some assumptions about how ChronoGraph worked, and it's actually not the way it works at all. So that was kind of a pleasant surprise. Have you thought at all about like alternatives to ChronoGraph? Like, what would somebody do if they didn't have something built this way, that was purpose built? How hard is that? Have you thought about that at all?
The short answer is extremely hard. If you remember, I showed the example with SQL, right? That's the way you would do it in the SQL world. In the graph world, I've seen one paper during my entire PhD period where somebody tried to implement version control on top of a regular graph database, right? And the way that they did it is you have vertices, like your regular vertices, and whenever a new version comes around, you create a new version of that vertex and insert it. And then you connect them up with history edges. So each vertex gets a predecessor edge to the predecessing version of the vertex. The problem comes in, how do you version edges? Because you cannot draw an edge between edges. And then you suddenly have to do things like represent edges as vertices in order to be able to link them up again. And it's really wild. So I would welcome you to give it a shot, but I guarantee you will give up after 2 days or so.
Fair enough. Looks like we do have a question from the chat. I'll get it here. Why was a B plus tree structure chosen for the key value store? And because of the Exodus backend. What if I chose another backend?
Sure, feel free. The B plus tree is provided by Exodus out of the box. By now, they also have a second implementation for the key value store, which uses prefix trees, so Patricia trees, which is very interesting. I haven't tried it yet, but basically any key value store will work as long as it's providing the correct sort order and the correct transaction control mechanism. Any would work. You could also use RocksDB, for example. The downside is, as long as you're working with the JVM, you're kind of constrained to implementations in Java. I tried implementations in C, but the Java native interop is just so slow that you lose so much performance, it's not worth it. And the only solution that we have that I'm aware of in Java that is really widely supported and widely used is Exodus. For fact, yeah. I remember back in the day when we were still using Titan in texture, we used that for a while. There was this persisted library. I don't know, Stephen, do you remember it? which was also an embedded key value store, and Titan was built on top of it. Unfortunately, support for that was dropped eventually. So that would have been an option, but I think it's no longer around.
Yeah, I don't know what the latest is with that, but I do remember what you were talking about there.
Yeah.
Okay.
So basically, you're not constrained at all to B+ trees. You can use prefix trees. You can use whatever. Feel free to give it a shot and implement your backend.
Cool. I think the thing that maybe surprised me a little bit was that you had made use of the TinkerPop API, the threaded transaction API, which not many graphs do at all. There's maybe 2 or 3 that make use of it. It's definitely more of an embedded function, and I don't know. For whatever reason, I sort of expected this to work by way of like traversal strategies and just you sort of modifying the query to include appropriate filters and encode all this data in the graph structure itself, and like you came with like a completely different sort of model. So that was the part that I think was kind of surprising to me. You had this branch manager API and kind of a Git-like way of getting the data. So I thought that was, like I said, I thought that was kind of interesting that you use that. But you definitely have like your own API elements built into and on top of the TinkerPop Graph API to do this. I wonder, and I think the reason I bring that up is I just wonder, this kind of precludes ChronoGraph from being used in a remote fashion, which is sort of popular today to some degree. I mean, you could use it if you use scripts and sent Gremlin scripts to the server that could access that API. Yeah. I was just wondering if have you tried using this in any fashion, like in a remote fashion, or are you aware of anybody who has?
I actually played around a little bit with GraphQL. So I built a GraphQL front end. So I built a little server which basically runs just ChronoGraph, slapped the GraphQL interface on top, and that actually kind of worked. Like you said, you have to send the Gremlin scripts, of course, to access the custom APIs, but also the custom APIs can be accessed through GraphQL, because GraphQL you can expose whatever endpoints you want, basically, like a REST interface, for example. So I wouldn't say that having a custom API on top precludes you from remote access. It just precludes you from using maybe the standard Gremlin server components. That might not work. That is true.
Yeah. Well, one thing you might consider going forward is, TinkerPop recently in newer versions, I think it started in 3.6, has a call step that lets you call custom functions. If you combined that with the with configuration step, you might be able to make this all work with pure Gremlin without, like, you could hide all of your, hide a lot of the custom lower level APIs and basically have a pure Gremlin API. And the advantage of that would be to be using the pure Gremlin language would allow allow folks access to code in other languages off of the JVM, right? Like, so they'd be able to code things in Python and connect with Go and all that sort of thing. So call step and with step might be interesting things for you to perhaps take a look at.
I'll check it out.
Looks like Fast Coder has another question. Let's pop that up. What's your experience with loading time when loading larger graphs?
I would say that Exodus does a fairly good job at handling large amounts of data, so the startup time is not terrible. You can run into issues when you have to do things like recovery and so on, where the entire thing has to be scanned again, but in general, it's doing a good job at it. Like I said, since we're dividing the history into individual chunks, and we know from the get-go which timestamp you're interested in, we only have to have a look at one of those chunks to answer a query, right? The worst case is when you are sitting on a branch and the query you're asking the system cannot be answered with the data from the branch alone, and we have to redirect to the origin. That's like the worst case you can have in terms of loading performance. yeah, and like I said, since it's all embedded, since it's all inside your application, you can even do things like load 1,000 vertices one by one from the database, and you will hardly feel the difference, really. So that's a big advantage over a distributed remote system. I guess that answers the question, kind of. It also depends on how do you define larger. So if you have 10 million vertices, I never tried that. So the largest graph, like I said, that I'm aware of that is used in production right now has around 400,000 vertices in one version, mind you. Yeah.
Cool. I think that answered the question. I guess if you could go back to your, maybe one more thing for me, if you could go back to the slide with your wish list, I'd love to just look at that one more time.
Yeah. I thought if I have the chance, then I will just post that.
No, I love it when folks ask for things. Like, we don't always get a lot of feedback from folks unless something's like really, really broken and terrible. So it's nice to hear when there's like an easier way to do things or suggestions or easier ways to do things. I mean, I do know about the union thing. We did talk about the kind of the type predicates, which is both those things are kind of in the pipeline, I think. You can do for number 3, there are options starting in 3.6 to be able to do that a little bit better. You do have to implement, so the Java based test suite, which we've always had, has kind of been unified now behind the Gherkin based test suite, which you have to kind of implement separately, like it's something new. It's the same tests in there, but it's all unified behind one test suite. So we use the same Gremlin test suite to test Java, to test Go, to test everything. So we don't just have like the single, like that JVM only suite anymore. I mean, it's still there, but we're mostly adding tests to the new feature test suite. So with that, you do have some options, like you can add, you can run a single test by adding just I think a system variable or something like that, and you can like lock it down to just that. So, and that works in IntelliJ like really nicely. So that might help you a little bit when you upgrade and head to 3.6. I think predicate optimizations, I think we're always looking for more of those. I don't know if if those in particular are ones we have or don't have, but I mean, we always kind of look for ways to like kind of unify all those things. So yeah, if you had more ideas about what those optimizations should be that we're missing, then yeah, I think maybe creating an issue for that in Jira would be helpful. And then the last one, I think, yeah, for sure. I think as you kind of know, you mentioned here, cryo is kind of a problem. I think Gryo is less of a Gryo's kind of been removed as a network serialization feature as of 3.6. So it's only used now for like just writing to the file system. And I think ultimately we'll probably upgrade to the latest one. It's going to take a breaking change, but for JDK 17 support, we have to move off of the old version 3 anyway. But I think that Gryo in general is probably not going to be around a ton longer. I don't know. I mean, it may be here for as long as 3.0 is around, which should probably be for a while anyway. But as you mentioned, this 4.0, yeah, probably be gone. And Jackson, that thing has always had CVEs. I think we keep up with them pretty well in TinkerPop. Like, they're constantly being fixed and upgrade. I mean, we must upgrade them 3 or 4 times in a release cycle.
Yeah, I know that feeling.
Yeah, so yeah, that thing is a pretty big problem. I don't know that we have like a particular solution for that, but yeah, I don't think anyone's proposed to actually have that removed yet. But yeah, I'd say if you think there's a better library out there for handling JSON based stuff, that might be worth discussing.
Not necessarily a better library, but I was wondering, why are you shading it? Why are you not just doing a regular dependency, like a regular?
Good question. I mean, in the early days, we thought shading was a good idea because it constantly conflicted with so many libraries, because it's used in so many places and people were pinning. Nowadays, you're upgrading so constantly, everybody has to be on the newest version. And I think that's where shading started, was like, this is always going to conflict. Like these Obgenesis always is a problem. And I think we have I don't remember what other ones are in there, but Obgenesis, Jackson, and Cryo are all shaded. So
don't get me wrong, I'm not opposed to Jackson at all. Jackson is a cool library, but please stop shading it, please.
Yeah. So I don't know. I think shading might not be as neat as it once was, like many years ago when we started doing it. We've had multiple requests to like just not shade these libraries. So maybe we should consider dropping Gremlin shaded altogether, and just folks should just deal with their conflicts the way they need to, right? There's plenty of I mean, we already use whatever that thing is, that Maven plugin that checks the checks and ensures like there's no conflicts and stuff on the path and all that. So if you're doing that, then you should have ways to resolve these things without us getting in the way with shading. Shading has other problems too. Like if you have existing Jackson stuff, like it won't plug in well. We had to do all kinds of things years ago to get shaded Jackson interoperating with the Jackson over in Spark and things like that. So yeah, kind of agree that maybe shading's not such a good idea anymore. Let me see. Doesn't look like there's any other questions from the chat at this point. And I think I've kind of gone through all the items. I actually had a lot more questions, but then as you went through your presentation, you kind of covered all the things. So I think this was good. I think everyone, I think there was a lot learned here. You put a lot of great information out here, and again, thank you for joining today.
Thanks for having me. It was my pleasure.
All right. Well, take care, everybody. Until thank you for joining the stream, and we'll see you all at the next one. Take care.
Bye bye.